We reiterate that the Bernoulli equation is v square by 2 plus gz plus p by rho is constant along a streamline if, and these are a long list of conditions, the flow is steady, the flow is incompressible, the flow is inviscid, there is no energy extraction, energy supplying device in the system between points 1 and 2, and there is no thermal action within the fluid, no heat generation and no heat transfer. The last two conditions are easy to see, and usually no mistakes are made in this. The flow is inviscid. This is the condition because of which many errors creep in. But the most of the errors are there because of the condition in the red, that is, the 2 points must be along the same streamline and that the flow is steady. Professor Julius Miller is a famous educationist who prepares a lot of videos to teach fluid mechanics, and in his pictures there are a couple of examples that is given where the phenomena is right but the explanation following the Bernoulli equation are wrong. The two examples are shown here. One is the atomizer and the other is the chimney.
An atomizer is a tube that resides in a vessel, and here is some liquid, and here is a tube across here, and here is a bulb, and you squeeze the bulb, air rushes across, there is a reduction in pressure, the atmosphere pushes the liquid up, and then the liquid is caught in the airstream and comes out there. I have often thought that the reason that's called an atomizer is because little atoms of the liquid come out there. Don't you like that idea, little atoms? Now, here is an atomizer, and spray would come out there. Now, I'm going to show you an atomizer on large scale. Watch it. This is fantastic. Here is a tin can, and here is a tube quite like that one residing in the atomizer. And I'm going to blow a stream of air through this tube. There will be a reduction of pressure in the tin can. And now what will the atmosphere do if the can has less pressure inside? The atmosphere will collapse it because it is enormously strong. Watch it. Watch. There it is. Here is my fireplace. My fireplace is a vessel with some puffed rice. Here is the chimney. I'm going to blow a sharp stream of air across the top. The pressure will be reduced here in this region. The reduction in pressure will be felt in the tube, and the atmosphere will push it up. Watch it. There it is. My chimney has an extraordinarily good draft. Watch it. There it is. I say that's a terrific.
Both these examples make the mistake that for Bernoulli equations to be true between 2 points, that the total energy at the 2 points must be same. The 2 points must be on the same streamline. Let's simplify the picture. We have a flow in an atomizer taking place like this. Professor Miller says the pressure just above the vertical limb is much less than the atmospheric pressure because of the larger velocity there. But where are the 2 points in which we are applying? If we say this is point 2 and this is point 1, yes, the pressure at point 2 is less, but less than 1. But what is the pressure at 1? It is not atmospheric. So we cannot say the pressure at 2 is less than the atmospheric pressure. And clearly, this cannot be the explanation why the liquid rises up the tube. The Bernoulli would not explain. There is another example that is given for Bernoulli equation. They take a slip of paper and put it against your lips like this and blow air. And as you blow air, you would see the slip of paper would rise and become horizontal. This is the jet of air that comes out and the paper becomes horizontal. The explanation given is because a larger velocity there, the pressure is less, and because the pressure is less, the paper rises. Pressure is less, but less than what? We have to follow a streamline, and if a streamline, the streamline of air would come from within the mouth. And the pressure there is not atmospheric, the pressure there is more than atmospheric. So there is nothing that shows the pressure at 2 should be less than atmospheric. So that will create a lift on the paper. So clearly, Bernoulli equation is the wrong explanation for this phenomenon. What is the actual explanation? The jet entrainment. As a fluid exits from a jet, it expands. I've shown the velocity profile at 3 locations and the streamlines. You see the flow is being entrained in the jet. From the side, it goes in there. Why does it do it? Because of viscous action. The jet coming out of the orifice drags the surrounding air into it, and the surrounding air starts moving. As the surrounding air starts moving, if we block the surrounding air, then the pressure there would reduce. If there is no blockage, the pressure throughout this region is atmospheric. There is no suction. The air is not moving upwards because of the reduction of pressure, but because of viscous action. The blockage does not let this air move in from below, and so there is a reduction in pressure because of blockage and the viscous action combined together. So these are viscosity driven flows. A Bernoulli equation would not really apply. Another example, consider a projectile moving to the left through atmosphere, which is stationary, and the pressure P atmospheric all around. What is the pressure at the nose of this projectile? If we apply Bernoulli equation to this, at a point far stream, the atmosphere is stationary, the velocity is 0, so pressure is P atmospheric. At the nose, the air particle is moving with the velocity of the projectile, velocity V0, and the pressure is to be determined. If we apply Bernoulli equation between these 2 points, I get P2 minus P atmosphere is equal to minus 1/2 rho V0 square. That is, the pressure at point 2 is below atmospheric pressure by an amount 1/2 rho V0 square. This is clearly against the observed phenomena. The pressure at the nose of this projectile is always more than the atmospheric pressure. So where have we gone wrong? This projectile is moving fast at a large speed so that the Reynolds number can be taken as very high. We are on the same streamline. The velocities are written correctly. So where have we gone wrong? Where we have gone wrong is that the flow is not steady. Bernoulli equation applies only to steady flow in the form that we derived it. So, we have to make flow steady before we apply the Bernoulli equation. How do we make this flow steady? By changing the frame of reference. Let's attach the frame of reference with the projectile. And if we do so, the projectile becomes stationary and is the atmosphere moving past it at a velocity v naught far away where the pressure is P atmospheric. Then far away the velocity is v naught towards the projectile, pressure is P atmospheric, or at the nose of the projectile the velocity is 0 and the pressure is given by Bernoulli equation now as P2 minus P atmosphere is equal to 1/2 rho V naught square positive. This is the correct solution. Moral of the story, the Bernoulli equation in the form that we derived is applicable only to steady flow. So unless we can ensure that the flow is steady, we cannot apply the Bernoulli equation. Thank you very much.